So now that we know how to do antiderivatives and indefinite integrals, we're now going to use that to begin to talk about solving something called differential equations. A differential equation, which we often abbreviate as a diff, D-I-F-F-E-Q, which we give the nice cute name, a diff-EQ, is an equation involving the derivatives of a function. It could involve just one derivative, or it could involve higher derivatives. In solving these problems, we're trying to find the function or family, often a family of functions, that satisfies the equation. Because remember, when you take a derivative, it's a definite thing, but when you go from a derivative backwards, it's indefinite. That's why we call it an indefinite integral. So, kind of like solving an equation, except now we're solving something for a function. So, we begin with an example. Our equation, let's say, is dy dx equals 7x cubed. So the derivative is 7x cubed. We want to figure out what would the function have to be. So it turns out what we're going to do is we treat that dy dx as if it's an actual fraction that we can break up. In fact, there's actually a way to do implicit differentiation that when you differentiate a y, you attach a dy. When you differentiate an x, you attach a dx. And then you got to get the dy dx's together as a fraction. And it turns out that's equivalent to the process that we use. So what we do is we take that dx and we multiply it over to the other side so that it's with the x's. So we have dy equals 7x cubed dx. And now we can say, hey, we want to find out what y is, so we can integrate dy. If we integrate one side of the equation, we should integrate the other side so that we still have a maintained equation. So we do that. Now the integral of dy is just y. And then we integrate the other side. So, well, I can pull the 7 out, that's a constant. And then I have integral of x cubed dx. So now back just using my power rule again. So I'd add 1 to the exponent, become a 4. So I'm going to divide by it, 4, and I'll have an x to the 4th plus a constant c. Now when we have a solution like this that has that constant with it, that's called a general solution. Or if you prefer, it's generic. That's the whole family. It doesn't get us really down to the nuts and bolts of what happens. And it's called a general solution. However, if we have some initial values, say for example, I know that f of 0, I know that when x is 0, the actual value of my function, whose derivative is 7x cubed, the actual value of my function is 5, we can take that initial value and plug it into our equation, along with the fact that x is 0. And so we now have an equation that involves really one unknown and only, and that's the constant c. So we can then proceed to solve that equation for c. And now when we write the equation down with that actual constant, where we actually know the constant, well then that has another name now. That's not a general solution anymore. It's a very specific, or if you will, a particular solution. So we have two types of answers that will go with a differential equation. Again, the process is real straightforward for solving the equations that we're going to be solving. Which, by the way, these are called separable because you can get the y stuff on one side, the x stuff on the other side. The basic process is we get the dy and any y's on one side, get the dx and the x's on the other side, and we integrate. It's just finding any derivatives. So it's nothing really new. New stuff here is that we have these two types of answers: a general solution, generic. If we don't have any extra information, that's our generic answer, and that's the best we can do. If we do have additional information, we can solve for what's called a particular solution. Now, in our next example, we're going to look at where that old fun position function came from. How does it come about? Okay, and it's based off of the fact that acceleration is the second derivative of position. So that's coming up in our next video. See you in a few minutes.